welcome to the tutorial solution for extension section question 4. So basically, question 4 requires you to watch a video titled Simple Python Modeling to sort of give you an understanding on how to approach modeling process or simple modeling processes in this case in Python. And it's asked us to apply what we learned from that video to the newly rearranged data, which is the data we rearranged in question 2, which is the M sorted and F sorted. It's okay if you've named your rearranged data a different name to me, that's fine, as long as you can keep track of things. So now we're going to try to walk through question 4. So just make a quick note here, question 4. So essentially what question 4 requires us to do is to make use of the NumPy library and the function in the NumPy library called polyfit to essentially create a mathematical model or mathematical equation that describes the relationship between our force and our mass. And in this case, before you apply a mathematical model to something, you need to have some sort of idea or like an inclination of what the equation would look like. And if you remember from question 3, we rearranged our data as you can see on the screen here, and we went from this graph that makes no sense to a graph that kind of makes sense, which is the fact that like it's almost a straight line. And if you look at the scatter plots of this graph, you can see that like it follows a straight line trend. And what this question is trying to make you do is carry out the procedure of line of best fits, which is what you normally do on paper in your maths and GCSE. But in this case, it's trying to get you to do it with Python. So because we understand and know from our scatter plots and the rearranged data that the equation we're expecting to get is some sort of straight line equation, which is y equals mx plus c in this case. So we can then apply the polyfit function in Python as follows. So we simply say I can call my model. So I can call my model in this case fit, so which is just for like fitting, and I can say this is the application of the polyfit function in NumPy, and this polyfit function allows you to apply polynomial equations to a data set. So the data set we're going to be applying it to is our M sorted and F sorted data set. And when I say polynomial, it means x to the power 4, x to the power 5, all the way down to x to the power 0 in this case. So basically, the polynomial function would take the data and fit a polynomial equation to it. And our polynomial equation, for example, can be a quadratic equation, a straight line equation, or a x to the power 3 equation, x to the power 4 equation, or even x to the power 200 equation, like to go a bit wild. But the idea is that the polyfit function would take the data and calculate the coefficient from, let's say, x to the power 3 and then calculate the coefficients for x to the power 2, and then calculate the coefficients for x to the power 1, then x to the power 0, all the way to get the mathematical equation that describes our process. And polyfit allows you to state the maximum order. So when we say order, so the order means the highest power in our equation. So let's say we wanted to fit an equation to a data that shows a quadratic profile. We would simply say the order is 2, because that is the highest power in our equation. So x squared plus x plus a, because where a is an ordinary number like you would have in your regular quadratic equation. And let's say the order is 3, that means the maximum power in our equation is going to be 3. So that's going to be an equation that states x to the power 3 plus x to the power 2 plus x to the power 1 plus c, that kind of thing. So in this case, because we have an inclination or like a prediction of what our equation should look like, we know it's going to look like a straight line. So that means the highest power in our equation is 1, which is x. So because we would have the equation y equals mx plus c, so the power of the x there is 1. So that is the highest power in our equation. So we know our order is 1 in this case. So to apply what I've explained, we would simply say fit equals np dot polyfit, which is the polynomial function that fits a mathematical equation or model to our data. We can then put in what we call argument, and argument is basically a set of data or instructions that describes what the polyfit function should do. So our x data in this case is m sorted. Our y data in this case is f sorted. And then we want to include the order, and in this case it's the equation of a straight line, and the highest power we have there is x to the power 1. So our order in this case would be 1. Then what we can do is then run it. In this case, when we run it, we can then go to fit, and you can see we have 2 values there. So what this gives us is the coefficient in our equation. So we've applied a straight line equation, y equals mx plus c, and how we've applied that is by stating that the maximum order of the equation that fits the data m sorted and f sorted is 1. That means x to the power 1 is the highest. So what this gives us here is essentially the coefficients in our straight line equation. So we have y equals mx plus c. So in the order they appear, that is what we get here in the equation. So we have y equals mx plus c. So we know m is the first coefficient, so that would be our gradient as well, and c is also another coefficient which describes the intercept with the y-axis. So in the order of that equation, the coefficients are m, which is 9.75156189, and c is 7.1521541. So what we can then say is that we want to save that equation in the form of f of x So which is something you would have heard in class, where f of x basically means a function of x, and in this case our x is the m sorted data. So we can just simply say that equation equals numpy dot poly 1d. So that basically means, so bear me one sec, I'll explain. Equals fit, so we put fit in there. So basically what we've done is save this equation here that we got in the form of y equals mx plus c as an equation by using the poly 1d function in numpy. And what that does is that it allows us to save our equation as a straight line function, which is f of x equals, as you can see in this case, f of x equals mx plus c. So we can just save that in this variable called equation, so that we can use it to do calculations somewhere else. So what we can then do is print equation to see what the numpy dot poly 1d function does to our model. So we can do that. So let me clear up my workspace before I run it. So if we run that, you can then see here that we get the equation of a straight line, which is what we've saved as f of x equals mx plus c. And as you can remember, I said previously that the coefficients are given in the order they appear. So in this case, m appears first, then c. So m is our gradient here, 9.752. As you can see in the results we're given in the numpy.polyfit function or operation we carried out here, you can see that 9.751 is the first data point we get, which is the gradient, as you can see, mx plus c in this case is 7.152, and you can see it's the same here. So that is how to save equations, or more specifically straight line equations in this case, so that you can then call on it to do things further down in your code. So an extra thing you can do here, just to be fancy and to really present your data well, is to plot this equation which we've saved here using the name equation. You can name it anything you want, it's fine. We can then like plot this equation on our data so that we can compare how our model is to the actual raw data, and this would like give us that information of how our line of best fit sits on the data. So this is basically me trying to show how you draw manually your line of best fit on paper, but in this case on Python. So to do that, we can just simply create a new figure by saying plt.figure, empty brackets. Then we can go further to say, firstly, we want to plot our scatter points, so our scattered data. So we make use of the matplotlib.scatter function, and we put in m sorted, which is our x, what we want on our x-axis. Then we say f sorted on our on our y-axis. Another thing we can do, instead of writing, wait, actually no, let's carry on. I'll show it to you later. So we can put f sorted, and we can then put comma here and add a label because we want to state what things are on the graph. So in this case, I'll say label equals data points. Then I can then basically copy this, which is the same as our force axis and our mass axis. So XY label, all those like common things you would normally use for a plot, copy that in. Then I can clear my workspace, then run it to show you what we get. So you can see here in the terminal that the scatter plot is labeled data points because we've used the scatter function here and we've assigned a label called data points, and then the extra thing to display the label is that we've gone and put in the function called legend in the matplotlib library. So legend with empty brackets basically allows us to show whatever title we give a particular data set in our graph, and this is useful when we have a single graph that is showing multiple data, so that we can differentiate them, and you see what I mean. So now firstly we've plotted the data points. Now we want to plot our line that best fits, so we can then use plt dot, in this case we'll use the plot function because we don't want to plot it as data points, we want to plot it as a straight line. We can then say inside we can put in our m sorted, which is our rearranged mass data. Then what we can then do is, remember we saved our model function as in the form f of x equals mx plus c using this function. Yes, so we can then use equation, and equation in this case is the name of our straight line function that relates the mass and the force together. So we can then say equation in brackets m sorted. So what this essentially does is that it allows us to make use of our function without having to write it out. So it allows us to make use of the form f of x, where x in this case is our mass data. So we put in our mass there into the equation, and it should perform this expression on each value of the mass data. So it's basically going to say the gradient multiplied by each value in our mass data plus the intercept we got. Then that calculates a new force based on our model, and it should plot it automatically. So then we want to differentiate, actually no, I would let us plot it first. So we press run, and what we should see essentially is two sets of data. So our straight line, which is this, and our data point, which is the one in blue, which is this one's here at the top. So what we can then do is we can simply change the color of our line of best fits plot so that we can differentiate it from the data points themselves. So what we can then say is comma R. So R in this place means color red. So when I run it, you should see that the line has now changed to red. Another thing we can then do now is add a label like we did before to the straight line of best fit equation in this case, as you can see there. So to do that, what we can do is label equals, and we can then call it model. So remember, you need to use your quote marks, model, and we then say equals. Then we want to write our equation there, and remember we saved our equation using the name equation. So what we can then do to write it, we can then say plus, then str, which means string in this case. Then we can then put in brackets equation. So what we should then see is that when we run this, because we have the legend function here, the legend function works for as many plots you have within that same graph. So you just have to put the legend function once, and it should apply to whatsoever many plots and how many you have in that on that graph. So if we run it now, we should see that once it comes up, we have a straight line being recognized as model equals equation, and we've written our equation as a string, which is essentially a way of reading non-numerical characters, because we have that x there and that plus, so it's not a number. So using the string function allows us to read non-numerical values and write them wherever we want to. So now we have model equals the gradient plus x, gradient multiplied by x, plus the intercept, which is c, which is 7.152 in this case. So that is all you're required to do for question 4 in this case. Thank you for listening.